repeats a lot of what we've already seen, and I don't think we'll necessarily spend the time going back through the Grignard reaction again. It's very important, but hopefully we spent the time that we laid out the fundamental parts of it, and it'll make sense as we see it more and more. But what we want to do is start thinking about a couple of different reactions of aldehydes and ketones to set the stage for all of these different sorts of carbonyl compounds. So this beginning part is a bit of a review, I know, but let's just go through it because hopefully it'll help. So let's compare an aldehyde and a ketone. Now we already know what these are. We know an aldehyde is something that has one or two hydrogens on the side of the carbonyl group, whereas the ketone has two R groups. And hopefully now we're getting much more comfortable with these functional groups. And I'm specifically not going into the nomenclature. I think the nomenclature probably covered somewhat at the beginning of the first semester, at least to the extent that we should have to cover it. Now, when we look at this, we want to compare the reactivity of these two. And this is, I think, what was on that video a little bit, but I know. So we can compare the reactivity. And you go in the lab and you carry out some sort of reaction, not sure what it is, and you make the observation that we'll mark here. We say aldehydes are more reactive than ketones. And that actually is correct in general. More reactive than ketones. So then what we always want to be asking is, well, why is that? What could be a reason or reasons that we see that aldehydes are more reactive than ketones? And there's really two things that we could consider, probably. It's maybe more complicated. But one, let's consider sterics. So we can look at our aldehyde here that has these, I'm going to try to exaggerate, two little hydrogens there. And then we look at our ketone and just take something like acetone. It has two methyl groups. Trying to exaggerate a little bit here. And what we will notice is that, yes, and electron density, you're stealing my thunder, but you're exactly right. That's the next step here. So when we consider the sterics here, and then we'll discuss electron density next. Here, imagine having a nucleophile attack. It needs to have access to attack, as we were mentioning, from the backside of this aldehyde or ketone. And here we have these two little hydrogens, which are really not providing any sort of steric hindrance. However, even though it does still happen, and we'll see all sorts of reactions as we have with ketones, there is a little bit more of a steric hindrance here when we have these two larger methyl groups. So this nucleophile might bump into these groups a little bit more, which is going to make it slightly less favorable. Or let's turn that around and say the aldehyde is going to be a little bit more favorable. So this might be more reactive. It might react faster. So let's just say, make something up. Let's say same nucleophile, maybe the aldehyde reacts 10 times faster. So that's one component. However, as was mentioned as well, is that it's not just sterics, but there's also an electronics feature. And this is what those electrostatic potential maps on the video we're trying to show. Let's now change our aldehyde to acetaldehyde, I think. So when comparing hydrogen to I'm going to make that a somewhat straight line if I can. Oh, I erased too much. Let's try it again. About that, okay? Comparing hydrogen to a carbon of a methyl group, the carbon is actually slightly electron donating, and this will come up in a lot of other cases as well. So that if we were to draw a bit of a dipole here, this methyl group is slightly just electron donating. Which means that's going to make this carbon here slightly less electrophilic. The more electrophilic it is, the more reactive it is. So imagine this here now is just a hydrogen from aldehyde, the one on the above. We don't really have anything that's electron donating. Now if we replace that hydrogen with a methyl group, it's slightly electron donating, which will make this carbon slightly less electrophilic, and as such, potentially slightly less reactive. reactive. So that's the logical progression. Now, let's think about the same thing with acetone. We'll just use the same one, acetone again. Now we have two slightly electron donating groups here. And so those are both slightly electron donating. And so we have, we'll say more electron donating. That reminded me, this is completely off topic. Oh no, I'm forgetting the number. It was the commercial, I think it was for Flonase, the drug. Is it? I forgot what they said. It's either 3 is greater than 2 or 6 is greater than 5 or something like that. And I thought, yeah, well, that is right, certainly. In this case here, if one group is slightly electron donating as an alkyl group and reduces reactivity, and then you have two groups that are slightly electron donating, that should reduce reactivity just a little bit more. Okay? So those are two reasons why oftentimes aldehydes will go this direction. Aldehydes are more reactive than a ketone. It doesn't mean the ketone is not reactive. It's just that it's relatively less reactive compared to the aldehyde. All things else being equal. Now, this a lot of times will be apples and oranges comparisons because there's a lot of other features. Okay, so then going forward, let's compare now, instead of an aldehyde and a ketone, let's just think about a general mechanism of a reaction. And this is actually what I had on that video, but as well. But I think I'd like to go through this together here just because it's going to be so important. And so if you watch the video and you say, okay, now why are we going through this again? We won't do this often, but just in this particular case, and every other time we do it. But just this time, hopefully it's important. So this is going to help with a lot of the carbonyl chemistry that we're dealing with. Two general mechanisms. The first one is the one that we've already seen quite a bit with a strong nucleophile. And I'm going to use the same example because it's consistent. So let's try to spell things right. So under basic conditions. And in general, what you'll see is basic conditions are a little bit easier. Basic is more basic. So basic conditions. Let's take let's just use the same formaldehyde that I used last time so we don't have stereochemistry. We have our aldehyde or ketone. We have a strong nucleophile, Grignard reagent or hydroxide in this particular case. And now we know from our discussion from the past couple of days that this carbonyl carbon is electron deficient. Our nucleophile can attack. In this case, it can attack either from the top or the bottom of this trigonal planar sp2 hybridized system. We'll just put it from the top out of simplicity here. And this is going to lead to this intermediate. So CO. Notice now I'm actually drawing these bonds pointing down because it's going from, meaning the carbon is going from sp2 hybridized trigonal planar to sp3 hybridized tetrahedral. And now to finish this reaction, what we need to do is we're going to protonate that oxygen. Let's have water protonated like this. And we're going to add one more thing here in a minute. So let's now draw our final product, protonated. Like this. And then on the other side, we've generated hydroxide. So we've made another hydroxide molecule, which can actually go back and attack another aldehyde and on and on. This one now is still sp3 tetrahedral. Now, one or two other things is sometimes we're a little lax in this, but these reactions actually are all in equilibrium. So I'm going to put those as equilibrium arrows to help highlight that. So if you have a aldehyde like formaldehyde, actually formaldehyde exists primarily as this species over here, where we've added water across the species. And that was one of our next reactions, but since we have it here, we've actually made the hydrate. But for this particular case, I think it's more important to focus on this general mechanism. This strong nucleophile on the left here, this hydroxide, can be a variety of nucleophiles. It could be OH minus, SH minus, Grignard, other things that we'll see that are carbon or nitrogen nucleophiles. And so this is the key thing. But notice again, nucleophilic attack, tetrahedral intermediate, protonation to generate our final product. And then last, strong nucleophile. So negative formal charge on the left, negative formal charge, negative formal charge. And we want to do that to compare that mechanism. Oops, screen. To rather than with a strong nucleophile, a weak nucleophile. And generally with a weak nucleophile, the reaction is going to be so slow that you won't actually see hardly any reaction. So what we're going to do is add just a drop of acid. So this will be, as opposed to basic conditions, this is going to be under acidic conditions. This reaction mechanism is a little bit more complicated, but hopefully makes sense when we look at it here stepwise. So let's use the same aldehyde. And if we wanted to react this with water here, the reaction will actually happen, but let's just imagine it's going to be quite slow. So now what we'd like to do is to increase the rate of the reaction. So what we're going to do is have just a little bit of acid around. And I'll come back to this later. Right now, let's just draw this as H3O plus or hydronium. When in doubt in dealing with carbonyl compounds under acidic conditions, the first step is to protonate the carbonyl group. You'll see this time and time again. So we're going to protonate the carbonyl group. We need to save some space here. So let's now draw this. All this stuff is the same. Now what we've done is we've protonated the carbonyl group. And we still have a lone pair of electrons on here. Let's just put it here. And notice now we had oxygen here, which originally had no formal charge. Now that it's given up a pair of electrons to form that bond with the proton, that oxygen now bears a positive formal charge. What this does now is we could actually draw a resonance structure. Squeeze a little arrow in there. It's not the most clear. I'm going to erase too much, I think. Well, it's because I have the eraser on the big one. Let's make this smaller. There we go. Not sure if that's much better. But we can actually write a resonance structure where we move those electrons up onto this oxygen. Like this. And we have a positive formal charge on the carbon. So unlike this species above, and going all the way back to the upper left, we could also draw a resonance structure here where we move these electrons up onto this oxygen and have a positive formal charge on the carbon. But the major contributor is going to be what the species has shown here, without any formal charges. However, on the bottom here, one of these two atoms does have to bear a positive formal charge in both of the resonance structures. So it's going to be predominantly, this will still be the major contributor because everything has an octet. However, this protonation really makes this species much more electrophilic because now there's much less electron density. That oxygen is donating some electron density to the proton. And this is what's known as this oxonium ion or oxonium cation. And that's the species that's more electrophilic. What this does is you've made this compound more electrophilic. So now our weak nucleophile, like water, so I'll just disappear it off the side there, is able to attack in a reasonable rate this weak nucleophile. And that's going to then lead to something that looks like this. So let's put the water on the top again. And I'll fill in a formal charge in a second. And now notice what we did is we started with a species that has a positive formal charge here. Water is attacking, so we still have to make sure we take into account our formal charge. And this oxygen now has a formal charge of +1. And then one more step is we need to deprotonate this Use another water molecule. Let's take this proton off. It's going to take care of that formal charge. Would have been nice to have this going from left to right, but I don't think I have space. Hopefully on your paper you can just maybe put it over here. I'll try to scribble it down here. OH. We'll just keep it on that side. Plus H3O plus. All right. So that's the final product. Now for this one, note the general mechanism. When we have a carbonyl containing compound, we'll see this is with an aldehyde. It can also occur with ketones and a variety of other functional groups. Under acidic conditions, the first thing we're going to do is protonate the carbonyl group. That makes this carbonyl containing compound much more reactive. So that now our weak nucleophile, which is water in this case, can attack. Could attack from the top or the bottom. I'm just showing it from, looks like the top. Generates now an intermediate that has a positive formal charge, and then we deprotonate to generate our final product. I'll make this a little bit smaller so we can compare the two. Something you'll notice is that circling down here on the bottom, our product is the same as the product on the top, despite being poorly drawn in slightly two different ways, but it's the same product. So there's two mechanisms to get to the same product. The one is with a strong nucleophile under basic conditions. The other is a weak nucleophile under acidic conditions. And just like we mentioned, it's a negative formal charge on the top, negative, negative, negative. Under acidic conditions, it's positive, positive, in the resonance structure, positive, and then positive. So James asks, is the purpose of the acid is to make the carbonyl carbon more electrophilic, right? And you're right. That's what it is. And so if we were to, I wish I could cover up with my thumb, if we didn't have acid around, this reaction might be really slow. The water will still attack, but it's a weak nucleophile. And then this is not quite strong enough, let's say, to react with that weak nucleophile to a large extent. Okay, right. And so then, however, if we protonate this, then we've made this species much more reactive, so we speed up the reaction. Something to note is that it's an acid catalyzed reaction. We start with acid, and we generate acid in the end. So the acid is not consumed in the reaction. And Angela asked, should we always use equilibrium arrows? The correct way to show it is to use the equilibrium arrows. And so I would encourage you to use them as much as possible.